This is Math 30-2, and we're in Chapter 6 looking at exponential functions and equations. So here, as we look at the second part of 6.3, the first part we looked at how do we solve exponential equations, where we can write the two sides of the equations as powers of the same base. So hopefully you have reviewed that, and today we're going to look at some application questions. So we want to be able to solve some problems using exponential equations. And here's our first question. Assume that your kidneys can filter out 25% of a drug that's in your blood every 4 hours. So before I read more, well, I guess we should read a little more. You take 1,000 milligram dose of the drug, and we want to fill in this table that shows the amount of drug in your blood as a function of time as time passes. So the first data points are already entered for you, and we want to round each to the nearest milligram. I don't know if I rounded to the nearest milligram or not, but you can as you're filling in the table. So you'll notice here that we started with 1,000, and I'm saying after 4 hours, there's only 750 milligrams left. Well, where is that coming from? Up here, we said that 25% of the drug can be filtered out in 4 hours. So there is 100% in your blood, and we're taking out 25%. And so that's giving us 0.75 is how much is left over in your blood system. So what we did here is we just took this and we multiplied by 0.75. And that gave us the 750. And then we're just going to keep that pattern going. We keep multiplying by 0.75 to get our next entries in the table. So I'm going to have you pause the video at this point and fill in all these values in your table. Now, this looks like it could take a long time, but it doesn't have to take a long time. Here's where your calculator can make life easy for you. So what I could do here is on my calculator, let's come back to my calculator. There we go. I could enter the 1,000. Now, right away, I could do times 0.75, but I don't want to. What I want to do is just hit equals or enter, because that has the 1,000 stored in as my previous value. And now when I do times 0.75, what my calculator will automatically do is it's going to multiply this to my previous answer. So now when I hit enter or equals, I get that 750. Now here's the trick. That 750 is my last entry. If I hit equal or enter again, my calculator will repeat that same calculation. And there we go, 652.5 milliliters after 8 hours. So that would be the entry that we would put in at this point in our table. What was that, 562.5? Did I remember that right? And I did say that you could round to the nearest whole number or nearest milligram. I didn't, but you can. Okay, so then you're just going to keep hitting enter and you're going to fill in all these values. It will be important for you to get these values because we need to be able to plot them in this table. So we want to have all of those values to plot in this graph and then look at the pattern that happens. So once you finish the table, you will plot the points on the graph. Once you've plotted the points on the graph, I'd like you to go to the next page, and there are 4 questions here that I'd like you to work through. So work through these 4 questions after you finish that first page, and then you can restart the video once you've finished all of those questions. Okay? Pause the video now, please. Well, here's my completed table. You'll see that I rounded to the nearest tenth of a milligram. That's not what we were asked to do. And so if you rounded to the nearest whole milligram, that's perfectly fine. And the nearest tenth, I can't graph that below here on my graph anyhow. I can't be that precise. So it really wasn't useful to keep that nearest tenth. But here's what I ended up with in terms of my graph, and hopefully you have something that looks similar. And when you see this, hopefully as well, you think, oh, this kind of looks like an exponential function. Now, as you think about exponential functions, in what situations did we have an exponential function that was decreasing as we went from left to right, where the left end would have been approaching a y value of positive infinity, and the right end would have been approaching this horizontal asymptote of y equals 0. What do we know about that exponential function? Well, we'll talk about that more as we continue on the next page. Question number 1. How many milligrams of the drug are in your body after 2 days? Well, we're looking at 2 days. Notice in our table here, this is a number of hours since taking the drug. 1 day is 24 hours, 2 days will be double that, so 48 hours. So this is what I'm looking for as my answer for that question, about 31.7, or if we did whole numbers, that would be about 32 milligrams being left in the blood system. So after 2 days, 48 hours, there are about 32 milligrams of the drug still in your body. Pause if you need to, but I'm going to continue with number 2. In the context of this situation, what are the domain and range? Well, let's look at the graph to help us out here. For a graph, we started for our domain, our x values, at a time of 0. And if we think about what's happening, time 0 is when you first took the drug. So was there more than 1,000 milligrams in your blood system before time 0? No, because it was at time 0 when you first took the medication. So values for x that are less than 0 will be useless in the context of this question. But we could imagine this continuing infinitely to the right. So our domain could be all real numbers to the right, but starting at 0 on the left. So greater than or equal to 0. Our range, notice we have this maximum value here where y would equal 1,000. That's the most of the medication we had in our blood system, and then it just decreased from there, approaching 0. But again, if we think of an exponential function, it never actually reaches 0. So in this context, times before the drug are taken are irrelevant, so the domain time is greater than or equal to 0 hours. And the range would be y values, or the amount of the drug in our system, would be greater than 0, less than 1,000. Well, this range leads to an interesting question. Again, pause the video if you need to take time to write this down, but I'm going to continue. This greater than 0 for the y value kind of leads to this next question. Will you ever completely remove the drug from your system? The math says we won't, but the math is a model. So we could say if this model is correct, there will always be a small amount of the drug still in your system. The question is the model actually correct? Well, at some point, if the model is correct, the amount of drug in your blood system will get small enough that it won't be measurable. Does that mean it's gone? Maybe. Maybe your body does actually clean it out. Or maybe there's still a trace amount in there, but it's just not measurable because we don't have a precise enough test. So the question is there a time at which this model breaks down and is no longer appropriate for this situation? And we don't know, given the information that we have. Well, suppose we have a blood test in number 4 that's able to detect the drug if there's at least 0.1 milligram in your body. How many days will it take before the test will come back negative, as in it'll say there's no drug that is left in your body, at least no drug that can be detected? Here's one option. We could keep adding values to the table and then count. So here in our table, we got to a point of 7.5 milligrams, and then we could just keep going on our table to see when do we get to less than 0.1 milligrams. So that's what this question is looking at, that 0.1 milligrams being the amount in your blood. Or we could create an equation. So notice as we constructed our table back here on this page, we kept multiplying by 0.75 time after time after time. And so if we were to try to figure out an equation, what happened? Well, here, to begin with, this is 1,000. And this is 1,000 times, I'll do brackets, 0.75. And then this next value is whatever we had there times 0.75 again. So it's the 1,000 times 0.75 twice. Here it was once, and I could even say that here this was 1,000 times 0.75 to the exponent 0, right? Because any base to an exponent of 0 gives me 1. So that would equal 1,000. So then we see this pattern here that this next one will be 1,000 times 0.75 to the exponent 3. So this is after no time has passed. This is after 1 4-hour period, 2 4-hour periods, and 3 4-hour periods. So I could have my exponent represent a number of 4-hour periods since the drug was taken. So that's one way we could come up with an equation. 1,000 times 0.75 to the exponent x, where x is the number of 4-hour periods since the drug was taken. Y would be an amount in milligrams of the drug that remains at that time. So notice it's really important that we define our variables x and y, because otherwise we could say that x is a time in hours, but that wouldn't be correct. It's a number of 4-hour periods. If we have an equation like this, then we could actually graph. So I could graph that function as y1, and then I could graph a second function, which is y is equal to 0.1, which is this amount that we want to see where are those two graphs going to intersect. At that x value, that'll tell us how many 4-hour periods have passed until we get to a point where we only have 0.1 milligram in our blood system. So let's look at those graphs. Well, here we see part of the graphs. Just ignore this third equation there for now. So here I have the 1,000 times 0.75 to the exponent x. So x will be the number of 4-hour periods. Y is 0.1. So here, my y value is only going up to 50, so I can't see my y-intercept, but I want to see where these two functions are going to intersect. So this could be tricky on your calculator because you're going to have to look to the right a fair ways before you can find that intersection point. Desmos is going to make this a little easier for me. I'm going to select this graph. Nope, not hide it. Select it. And then it actually gives me the y-intercept here and this point where the two graphs intersect with each other. So if I was to zero in there, kind of center that, and then do some zooming in, oh yeah, so there at that point, we can see that the red graph is above, intersects, and then over here it goes below the blue graph. So that is my intersection point at 32.016, so about 32. So what that's telling me is it'll be about 32 4-hour periods. So let me write that out here. So x equals 32, which means in about, I'm going to use the pen to make this a little neater for you to read. There we go. If x equals 32, that means in 32 4-hour periods, the amount of drug will be reduced to 0.1 milligrams in our blood system. So how many hours is that? 32 times 4 gives me 128 hours. So pause the video here if you need to copy that down. But I'm going to look at a second possible equation that we could use for solving this problem. Here's the second equation in green. Now this one isn't as intuitive, not as easy for us to create because we have a fraction in the exponent that x divided by 4. Trying to highlight here. Oh well, that's okay. So here this is saying x is the number of hours since the drug was taken. So this form of an exponential in an exponential equation, what this 4 in the denominator of the exponent means how much time passes in order for this decay amount or growth rate, whichever we're looking at, to happen one time. So here, this 4 corresponds to the 4 hours, and we're saying that in 4 hours, this factor of removing 25% of the drug has happened one time. Might be helpful for us to think about different x values. So suppose my x value was 4 in 4 hours. 4 fourths is 1, so I'd get 1,000 times 0.75. Oh, so after 4 hours, I'll have 750 milligrams left over. Suppose instead, this x value was an 8. So it's saying after 8 hours, 8 divided by 2 is, I should say 8 divided by 4 is 2. This decreasing has happened twice. So two 8-hour periods, nope, 2 4-hour periods will have happened. Sorry, that was a little confusing. So where that corresponds on our table is this entry here, where this 8 is my x value now, and the 2 is the result that I get when I do that 8 divided by 4. Okay, so that's how that second equation works. A little more confusing, but you can expect to see equations like that as we continue in this chapter. So it's important for us to take a little bit of time to slow down and understand it. So let's consider this equation now and where that would intersect with this y equals 0.1. So again, let's have a look at our calculators or at Desmos to see what's going to happen with these two graphs. So here you can see again in blue I have y equals 0.1, and now I have this equation 1,000 times 0.75 to the exponent x over 4. So that's this green function here, and I want to know where these two graphs will intersect. So when I highlight this graph, it shows me this intersection point here, 128. 128, that's the calculation we got from our first graph. But now remember our x value is representing a number of hours, not a number of 4-hour periods. So this x is the answer to the question this time. It'll be 28 hours when the amount of the drug in our blood system decreases to that 0.1. So we're getting this same answer of 128 hours, no matter which equation we use. Okay, let's take a couple minutes to review now, solving equations. So question 5 and 6, take a minute to solve those two equations using the ideas from the previous lesson. So you can pause the video now, work through those questions, and then restart once you've finished both 5 and 6. Well, for question number 5, things are set up well for us already. We already have power equals power, where the base equals the base, And so the exponent, x over 2, is equal to the exponent of 8. And then I can isolate this x by undoing this dividing by 2 by multiplying by 2 on both sides. Remember, if I multiply by 2, it's a 2 over 1. And so these cancel out. And we end up with x equals 16. Question number 6. Not quite so straightforward because I can't see that they're powers of the same base. This 32, well, 4 squared is 16 and 4 cubed is 64. So I can't rewrite 32 as a power base 4. So I'm going to think of powers base 2. And I can write the 4 as equaling a 2 squared all to that exponent x. And the 32 is the same as 2 to the 5th. How do we know? Well, we could just do some guessing and checking, dividing. We could say, well, where did x come from? I don't know. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2, 32. So I could just multiply it out in my head or on my calculator to get that 2 to the 5th. Well, I need to do one more step. A power raised to an exponent. Remember, I can multiply those exponents. So I have 2 to the exponent 2x on the left. On the right, remember, a square root is the same as an exponent of 1/2. That is important. It's come up a few times already, and we need to make use of it. Then I can do that same rule I used over here. Power raised to an exponent. I multiplied those exponents. Here I can multiply these two exponents. So we'll get 2 to the 2x is equal to 2 to the 5/2. Power equals power. Base equals base. So exponent equals exponent. Now, I'm going to divide this by 2. But there's another mathematical operation that's equivalent to dividing by 2, and that is multiplying by 1/2. And that makes it a little bit easier on this side, because I can say I'm going to multiply this by 1/2. Then it's more obvious that these 2's will get multiplied together in the denominator. So these 2's will cancel out, and I'll get x is equal to 5/4. So there's my answer for this one. You'll notice in the question it did say verify your answer by substitution. So for question number 5, if I plug that in, I'd have 6 to the 16 over 2. Is that equal to 6 to the 8th? Well, I don't have to actually plug anything into a calculator. 16 divided by 2 is an 8. So 6 to the 8th equals 6 to the 8th. Yep, that check works. Let's try it for this one. If I have 4 to the 5/4, is that equal to the square root of 32? Well, this one isn't so nice to do. So what I'd say for this one is plug it into your calculator, and you'll find the two sides are equal. Let's move on to the next page. Now, here are a couple questions that are not in your notes, but I think we need to do these questions to build up to the questions that are in your notes. So I should update your notes, but not quite there yet. So let's look at these questions and see how we would solve them. Hopefully you remember from an earlier lesson that I can't just take this 3 and multiply it to the 4. That would be illegal math because this 4 has an exponent. This 4 is being multiplied a whole bunch of times before the 3 gets multiplied in. The 3 is only multiplied once, right? It has an exponent of 1 there. This 4 has a whole bunch of 4s. We don't know how many because we don't know what x is yet. So I can't distribute that in. Instead, what I can do is I can say, well, let's get rid of the 3 on this side by dividing it out. because then I'll just have the power on the right-hand side, which will be 4 to the x minus 2. And that's where I want to get to, where I just have a power equals a power. Well, if I divide the 3 on the left or on the right, I have to do it on the left as well. 24 divided by 3 gives me 8. Is 8 a power base 4? No, but it is a power base 2. So this will be a 2 cubed. And then we have 2 squared to the exponent x minus 2. So what this question is giving us is really this first step. That's something new that we hadn't seen before. From here down, kind of all these future steps, we've done those in previous questions. Remember, at this point, here a power raised to an exponent, I multiply the exponents, so this 2 has to be distributed to both of those. Again, just a reminder, you need to be careful with that. So I have 2 cubed equals 2 to the 2x minus 4. Remember, we did the 2 times that negative 2 to get that minus 4. Power equals power, base equals base, so the exponent equals the exponent. I can add the 4 on both sides, and I'll get 7 equals 2x. Divide by 2, and x is equal to 7 halves. There's question number 1. Number 2. Well, I have a 9 and a 3 in my bases, or a 1/3. And kind of that little stumble there of calling it a 3 is a hint that a 3 as a common base is going to be useful, because I can rewrite this 9 as a 3 squared. So I'll have that exponent 2x minus 1. And this 1/3 I can rewrite as a 3 to the negative 1. So remember that negative exponent, put that base into the denominator. So if I want to take it out of the denominator, I can rewrite 1/3 as 3 to the negative 1. And that's really the key step that I wanted to highlight in this example. So from here down, it should be similar to other questions we've done. So I'd like you to pause the video at this point and work through this question, then restart the video once you've finished it. Well, I hope your next step was to distribute. So I have 3 to the 4x minus 2. Same thing on the other side. I want to distribute that negative 1. So we'll have 3 to the negative 3x plus 5. Power equals power, base equals base. So the exponent is equal to the exponent. I want to collect all the x's to one side. And I want to collect all the constants to the other side. So I'll add the 2 on both sides. And I get 7x equals 7. Divide by 7, and x is equal to 1. There's question 2. Let's try a few more questions. These are in your notes package. Number 7. I have a 2 as a base on the left. So I want somehow to make this a base of 2 on the right. Again, as I've mentioned before, when we're working with powers, there's often more than one order to our steps. What I'm going to do is I'm going to take this 4096 and give it an exponent of negative 1 to take it out of the denominator, because on the left, this 2 is not in the denominator. And then I'm going to think, oh, how many 2's are in 4096? So you may want a calculator. to do some guessing and checking. And what I think you'll find is that 2 to the 12th is equal to 496. Did I say 496? It should have been 4096. Again, I have a power raised to an exponent, so I'll multiply those exponents. And here's my pen. 2 to 3x equals 2 to the negative 12. Power equals power, base equals base. So the exponent equals the exponent. Divide by 3, and x is equal to negative 4. Again, we could verify, but I'm going to leave this one here. Maybe I'll fix up that line. X equals negative 4. Maybe I won't circle it. On to number 8. As I look at these two sides, here in this power I have a 1/3, so I know I can change that to a 3 to the negative 1. So a 3 as a base is going to be useful. But then I look at this 8 and I think, oh, what? 3 doesn't go into 8 at all. But I do have this number in front here. And so similar to the question we did kind of on that previous page we looked at, I need to divide out this 5,832. If I do it on the right side, I have to do it on the left as well. Now, as I'm dividing, well, let me just fix the right side. That'll be a 1/3 to the x plus 2. On the left side, what I want to do is I want to see if I did 5,832 and I divided it by 8, what would I get? So I'm taking this divided by 8, and then I'm going to do my numerator also divided by 8. And it turns out 8 divided by 8 is 1. 5,832 divided by 8 is 729. 729, we saw that number in our previous lesson. That's going to be 3 to the exponent 5, I think. Nope, not 5. 3 to the exponent 6. Yep. So this is 1 over 3 to the 6th equals 1/3 to the x plus 2. Now notice now this 3 in the denominator, this 3 in the denominator, I could work with powers where my base is a fraction. I could get it out of the fraction if I wanted. I could turn this into a 3 to the negative 1. But let's just see what would happen if I leave it in the denominator. Now, 3 to the exponent 6, we knew that was 729. 1 to the exponent 6 is still 1. So this on the left I could write as 1/3 in brackets all to the exponent 6, and it would be equivalent to that previous line. That only works when I have a 1 as that term in the numerator, but then I have a 1/3 to the x plus 2 on the right. Power equals power. Bases are equal even though they're fractions, which means my exponent is equal to my exponent. And I get, what did I do there? That should be a 2. Subtracting by 2, I will get 6 minus 2, x equals 4. There's question 8. Question number 9 is similar, but again, one step more difficult, because now we have a variable in the denominator of the exponent. So I would like you to start this question, maybe see how far you can go in solving it, and then restart the video when you need some help along the way. Well, I hope this was your first step to divide both sides by 2048. So here they cancel out, and on the right side I have a 1/2 to the exponent 36 over x. On the left side, I'm going to again divide by 4 on the top and the bottom because I'm expecting there to be a common factor of 4, and there is. So that gives me 1 over 512. 512, with some number crunching, we get to be 2 to the exponent 9. There we go. And that's equal to 1/2 to 36 over x. Just like that previous question, I have fractions on the left and the right. 1 to the exponent 9 is still equal to 1, so I could rewrite that fraction on the left as 1/2 to the exponent 9, equaling 1/2 to the 36 over x. Power equals power, base equals base, so my exponent of 9 is equal to my exponent of 36 over x. Well, here we have a couple options for what we could do. Let's say we're going to multiply both sides by x to get the x out of the denominator over here. So that gives me 9x equals 36. And then I can divide by the 9 to isolate the x. And I'll get x equals 4. So final answer, there we go. I said we had a few options. So here's another option we had where we had this 9 is equal to 36 over x. What I could have done is I could have said, well, let's imagine this is a 9 over 1. I want the x in the numerator, so I'm going to do the reciprocal of the right side. And if I do that on the right, I have to do it on the left, which would give me 1/9 is equal to x over 36. And then I would multiply both sides by 36 to get rid of this denominator. Here the 36's cancel, and I get x is equal to 36 divided by 9, 4 once again. So same answer, no matter which method we use. Okay, I'm going to stop this video here. That's been super long already. And then we'll continue on to finish this lesson in another video, which will be relatively short. Okay, that's it for the moment.